Okay, we're in section 15.2, and we're starting out looking at a subject, combinational logic. A combinational logic circuit can have any number of inputs and any number of outputs. And so here we have a combinational logic circuit depicted, and we notice here we have our inputs to the left, A, B, going on up to n number of inputs, and the same we have any number of outputs. The logic states of the inputs at any given instant determine the state of the output. So with combinational logic, the inputs will immediately determine what is in the output. And these are the circuits we'll be looking at in 15.2. Sequential circuits, which we'll look at later, will feature circuits in which outputs are not determined solely by the inputs at the same time. And here we have some logic gates. All digital circuits are based upon the interconnection of the various logic gates described. Complex logic circuits are based upon OR, AND, and NOT functions along with their derivatives. To the right are typical packages containing multiple gates, and they're typically packaged this way. So here we'd have, for example, here's one package and it's got 6 inverters in it. And here's another chip package, and this has 4 NAND gates. And these are just done this simply to make it possible to put more gates on a given circuit board. Okay, logic symbols. The standard and the IEC logic symbols for the various logic gates are shown below. And the IEC is for the International Electrotechnical Commission. And the ones on, let's see, the first ones here to your left and then this group to your left are the standard symbols, and then the IEC are the newer symbols. And they're kind of self-explanatory. Here we have an inverter, and you can see here we have in the little slash here, it means that inversion. The OR gate, this simply means the IEC is just has a greater than or equal to 1, which is basically what an OR gate does. If you have one input, then you get an output. Here we have a NOR function, same thing except that you have the slash for the inversion. Then this is obviously an AND gate. This is the AND with inversion, which makes it a NAND. And then equals 1 here would be the exclusive OR, because with exclusive OR, if you must have a 0 and a 1 to get an output. So these are, both of them are used in the industry. So if you come upon a schematic and it uses the IE symbols, just use those. If you come upon a schematic and it uses the standard, well, use those. But they're both out there, so they're both being introduced at this time. Though throughout this text we will use the standard symbols. Okay, gate conversions. 2 or more logic gates can be combined to provide the same function as a different type of logic gate. This is often done to reduce the total number of IC packages used in a product. So rather than having a whole bunch of different IC packages, you can just build a digital circuit with just one type of package, and you just use inverters to change it to the device that you need. And so we'll look at a couple of these. Here we've got NAND and 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 OR and NOR. And what you'll see in this diagram is if we just add inverters, we can change the outputs. And so notice here, if we have a NAND gate and we want to change this AND gate to a NAND, it's quite easy. Just add an inverter to the output, and that's quite obvious. If you add an inverter here, then it would be a NAND gate. And if we wanted to change from an AND to a NAND, we could just add another inverter. Now there would be 2 inverters here, but actually 2 inverters would put it right back to what it was before. But at any rate, you can go both ways. And the same would be true with these 2. Now you can also go this way, and this way we would add inverters to the inputs. Now if we have a NAND gate and an OR gate, and we need NAND gates. So what we could do, we could come down here. If we added an inverter here and an inverter here, let's look at our lot and see what would happen. Remember, with a NAND gate, if we had a 1 and a 1, then the AND gate would give us a 1, but since it's inverted we would get a 0. So why don't we check this out and see if that would happen here. If we had a 1 and a 1, then we would come in here, those would be both inverted to 0, so we would have a 0 out. Let's try one more. If we had a 1 and a 0 going in here, then the AND gate would produce a 0, but it would be inverted, then we would get a 1. So let's try that in this one as well. So if we had a 1 and a 0 going in here, then we would get a 1 out, so that would satisfy that one. So those two could be interchangeable, and the same thing would happen with these two. Let's jump to the next page and we'll look at going across. Now in this case we have an OR gate, and it says to convert a AND gate to an OR, we would have to add inverters to both inputs and outputs. So let's put an inverter here, and an inverter here, and an inverter here. So in this case, with the OR gate, if we had a 0 and a 1, we would get a 1 out. So let's see what happens here. If we had a 0 and a 1, then it would go into the AND gate. The AND gate would produce a 0, but it wouldn't be inverted, so it would get a 1. So let's see, if we had a 0 and a 0, we'd get a 0 out. In this case, if we had a 0 and a 0, those are both going to be inverted to a 1. This will output a 1, but it gets inverted, and then it's a 0. And so, anyway, and it would work this way as well. So the idea here is that you can transform one gate into just about any other gate, and then if you're building a given circuit, you do not have to have a whole bunch of different gates. You can just use one gate and fulfill all of your needs. So in this section we looked at gate conversions, and we looked at the logic symbols, the standard and the IEC. We looked at the actual appearance of some of these typical packages, and we talked about combinational logic and talked about how it was different from sequential logic.